We will now hear Dr. Hussein's update on the Freedom Systems Center. Dr. Hussein, the stage is yours.
All right, thank you, Ken. Thank you for working this out too. So good afternoon once again, everyone. So I'm back here to give you a little more elaborate update on the Freedom Center activities. So there was a good session with our panelists from the federal agencies, and hopefully you got some good information about the funding opportunities. So in the next 15 minutes or so, I will highlight the features of the centers in terms of our research, education, and industry activities. So as I mentioned, the Freedom's journey started in 2008 with the establishment of the Engineering Research Center to create this energy internet that allows the integration of renewable energy sources, storage, and usage, and which can be controlled in a seamless way. And as you can see here, the distributed energy resources could be the renewable wind or solar, or the storage in an electric vehicle. And we're also introducing these new loads, which is also in the electric vehicle. And these new loads are more and more DC, like in vehicles or data centers or the electronic loads. And the Freedom's energy internet is built around the few core technologies, which include the medium voltage solid state transformers, the circuit breakers, the distributed controls platforms, and overall, the controls work to provide an intelligent power, energy, and fault management. So aligned with these activities, we have divided the Freedom faculty research areas into 4 thrusts, which are the wide bandgap power electronics, the renewable energy systems, the modern power systems, and the electric transportation. So the faculty shown here includes the entire spectrum of people, experts, I would say, in these various fields, starting from the devices, where we have Professor Jay Baliga, to power electronics, where we have several faculty members, and then going into the systems area for power systems and renewable energy systems. We also have faculty working, like Professor Tang, working on the energy markets, Professor DeCarolis working on the energy systems modeling. The new faculty that has been added over the past 2 years are, let me just quickly introduce themselves. One is Professor Wenyon Tang, and one is Professor Jiko Pantich. I mistakenly put Wenyon Tang's name on Jaco's picture, so hopefully, and I don't, I need to correct that. So I apologize to Jaco for that. So the thrust areas, as I mentioned, are 4 of these. And in these, the various different activities are in the wide bandgap power electronics that starts with the devices to the SSTs, the power electronics, the high performance converters. And electric transportation area, it also not only includes the drives and the power electronics and the controls for vehicle systems, but also like the electric machines area. And it expands into activities both for automotive, ships, aerospace, power electronics, and you'll see some examples of those today. So in the modern power systems, we work on the distribution systems, the distributed grid intelligence system controls, cybersecurity, the economic modeling and market mechanisms. And in the renewables energy sector, it's in terms of the microgrids, the integration of solar and PV systems, as well as distributed energy resources and the management and control of these various systems. So among the Freedom Lab upgrades, you all know, like we have medium voltage power distribution system within the center. The labs are capable of 1 MVA power capability, but over the past year, during the pandemic, we've been working on those for some time, but we have added the 250 kilowatt energy storage in the Freedom microgrid that many of you already know has the 40 kilowatt of solar panels on our rooftop, as well as various inverters to integrate those into the building loads. And then we have also introduced the EMI test bed, which can do CISPR 25 and CISPR 1612 for automotive applications, as well as the MIL standards. It's compliant with those DO 160 mil standards 461F. We have added the partial discharge tester, which can test up to 120 kV. It's in a shielded chamber, and the measured results are in compliance with the IEC 60270. The new PREE's high voltage multi-layer organic substrate and module fab capabilities now lets us create very high density, high frequency, low cost circuits. Also, with this capability, high frequency pulsed partial discharge performance of new 40 kV per millimeter organic materials can be researched. So this moves us into high power densities that has never been seen before. So I want to highlight the contributions of our graduates. So here's a list of our FREEDM graduates. The PhD candidates are shown over here, and this is not the complete list. We have a lot more, and they're joining the workforce as well as going into academia. Many of those are going into our partner or industry members, but also they're going into other automotive industries, the new EV industries, as well as the systems industries, and the drives areas as well, drives area industries as well. So this is some more of those people, and I've also included the several master's students who have graduated under various faculty members in the center. And here also you can see, like I didn't mention the national labs, but we have ones going into the PNNL, and then one student graduating after graduation going to the Oak Ridge National Lab. Some of the master's students are also going into PhD programs of other universities, as well as we get students from other master's programs into our PhD program. So that recruitment process goes on every year. So among recognitions, you have already heard from Professor Rania Chakraborty, who is, of course, a FREEDM faculty member, now loaned to the National Science Foundation, serving as the program director of the EPCN program. And also I wanted to highlight the efforts of one of our alumni, Dr. Landon McKee, who started this company, Water Brothers Desalination LLC, along with Professor Wes Williams of University of Charlotte, University of North Carolina in Charlotte, and participated in this Waves to Water prize competition. So they went from the design stage to the adapt stage, and now they're in the create stage, where there are 10 winners left out of like probably 110 that started, to actually create, to build the full-size, first fully functional prototype. And then Landon is working hard to make this a success. And then we have lots of other recognitions, also faculty and students winning prize paper awards and in different events. And I don't have the list of all of them included in here, but we do recognize the contribution of everyone in the center. So FREEDM's journey started, as I mentioned, as modernization of the power grid, and one of the core technologies is the solid-state transformer. So today you will you'll listen in a session about the solid-state transformers, but also I'll give you some brief updates of some of these activities on the solid-state transformer. So a lot of faculty in the center and students are involved in the solid-state transformer activities. The efforts now has gone global in the sense that, like lots of other agencies, research institutions, universities around the world picked up solid-state transformer work, which essentially, got its momentum through the FREEDM Center in its early years. And as the research and development of these solid-state transformers progresses, we see three key areas where it can have contribution. One is in the power distribution system. Another one, which is probably more near term, is in the electric transportation sector. and then in the data centers. So this is just an example topology, but the solid-state transformer itself is a big system that provides the opportunities to work in various different areas of the technology. So such as like in the device level, introducing the wide bandgap devices that can be used for the design of these not just low voltage, but medium voltage and higher capability SSTs. And then there are various different topologies that can be used. So there is another innovation area on developing different topologies, and the modular multi-level topologies are now becoming more attractive. And then there's controls and communications within the transformer as well as externally to it. And then also how storage, load, and generation can be integrated into this to form a microgrid, or in other terms, we can call it a network of power electronic components working all together seamlessly for power and energy exchange. But there is, of course, various challenges in terms of the controls. There's isolation issues that needs to be handled, the packaging and cooling, and also the protection and the grounding. So these are the various challenges that we and all researchers around the world are working on. So this is an example of the solid-state transformer application in a mobile utility support equipment. So the PI for this project is Professor Bhattacharya, who has been leading SST development work and is very involved in this from the start of the FREEDM. This example here is showing for the first time that a medium voltage SST has been deployed at a pilot site by an academic institution, developed by an academic institution. So the medium voltage SST has been funded by the Navy and has been installed at a naval base in Port Hueneme in California for a mobile utility equipment to use. The SST is based on 10 kV silicon carbide MOSFETs operating at 7.2 kilovolt DC shown over here, and the low voltage side is 800 volt DC that delivers an efficiency of 96.8% at 10 to 20 kilohertz, and the capacity of this one is 38 kilowatts. The other example of the solid-state transformer in the transportation sector is the medium voltage EV charging station. So the grid interface is built around an SST topology, as you can see here, and there's a medium voltage DC distribution bus that is supposedly to deliver or service vehicles of different voltage ratings, 800 volt, 400 volt, 200 volt. So this is a project led by NC State, funded by the Department of Energy's Vehicle Technologies Office, with our partners, ABB and NIPA. And then also in the development effort, we are getting a lot of support from our member Danfoss in building up this 1 MVA system, which is really challenging. So you'll hear more about this in the SST panel session. But the goal here is to deliver 1 MVA system with high power density using silicon carbide devices at 98% efficiency. We are at a stage of like testing. We have tested up to 200 kilowatt levels, and then we are going to soon test this at 500 kilowatt level at medium voltage in the FREEDM laboratory. And eventually this will be deployed at a station, in a field deployed at a NIPA facility up in New York for field testing. We also collaborate with the Coastal Studies Institute under a sponsored program from them. We're developing a 10 kilowatt microgrid, which will built around a multi-port power electronic converter, with the help of which we can integrate wave energy generation, shown on this side, as well as integrate storage, and then be able to supply both AC and DC loads. And here also, at this node, it can be connected to the grid. So the controls developed are for autonomous power balancing among all ports. The hardware has been built with silicon carbide power devices and then DSP-based controllers. And the communications is enabled through another project developed REAPS platform. So REAPS stands for Resilient Information Architecture Platform for the Smart Grid. This is also funded by ARPA-E. And the PI for this project is Dr. Sergeant Lukic, and he collaborates with the Vanderbilt University for the development of this communications platform. So this is going to be developed and deployed at Genetsphere in the Outer Banks, hopefully by the end of summer, for demonstration as well as for tow testing of an energy harvesting kite, which is being developed by the mechanical engineering faculty under another ARPA-E program. And then also recently, the DOE's Water Power Technologies Office has awarded an Atlantic Marine Energy Center, of which CSI is a partner along with University of New Hampshire and then Lehigh University. And then FREEDM is also involved in that as in collaboration with CSI. And our goal there will be to develop this 100 kilowatt microgrid, marine microgrid, essentially scaling it out from the 10 kilowatt that we are prototyping currently. And then also I would like to mention that we are utilizing technologies developed within the center that has been already, patented. So I'll go quickly over the next slides. Here, we're showing the high power density power electronics program for Dr. Doug Hopkins. He has several ongoing projects in developing high density power electronics for packaging, collaborating with Dr. Bhattacharya and Dr. Baliga. They have a CETO awarded program. And then also he has developed this cascaded super cascode. And Dr. Hopkins will also host a session tomorrow. And you will be, I may be mistaken, it may be today. So you'll hear more about that, the packaging work led by Dr. Hopkins in that session. So Dr. Wenyoung Tang received this award from CETO for day-ahead probabilistic forecasting of net load and demand response potentials with high penetration of behind-the-meter solar plus storage. This gives you a highlight of the activity where he has broken it down into three thrust areas. And the impact of this is to address the common problems in the current methods, and the outcomes are supposed to exceed and achieve exceed the current performance levels and achieve high accuracy in practice. So I will not go into the details of this, so the slides will be there, and that these will be posted so you can look into the details or contact Dr. Tang for more information if you'd like to. So in the transportation sector, we are also working on developing these high power density inverters. So we started with this Power America project for developing wide bandgap based 150 kilowatt and then scaled up to 160 kilowatt EV traction inverters. So currently we're working with a company under a DOE project to develop a 250 kilowatt non-boosted all-electric traction inverter. And currently the initial testing and validation is currently going on in our laboratory. So these are, this is also another project on electric traction motor designs, high power density electric traction designs to achieve 50 kilowatts per liter power density. So that's the goal of this program, which is being carried out again under the sponsorship of Department of Energy's Vehicle Technologies Office. And there's an electric drive consortium that is working on those. And again, this is about like 5-fold increase in power density. And the other main goal of this is to eliminate the use of rare earth magnet materials, which are scarce and also suffers from price volatility. So in the education programs, we have we have 200, more than 200 students graduated, more than 200 master's students graduated. So we still have our MSFC program going strong, and now we have the wide bandgap power electronics concentration added. And the bachelor's program still has the renewable energy, electric energy systems concentration program going on. So we thank our industry members for all of their support and participation and collaboration. So we welcome our new members, Facebook, Henkel, who joined recently, and last year Danfoss also joined as a member. And we collaborate in various different ways in terms of individual research work or targeted research, or in general, like talent production, right? Like, so workforce training of our students, and many of our students work for internships in these companies, as well as get hired permanently in many occasions. So the last few slides are about the major research awards that has been received. So I will not go through them, but they will be in those slides. And this list is also not a complete one, so there's a lot more that has been won and worked on by the faculty members. So thank you all. If there are any questions, I don't know, Ken, if we have time for questions, we can. I can take some questions.
Yep. Well, we are right at time to switch to our technical sessions. So I would encourage people, if they do have questions, to send you an email or put them in the chat, and we'll make sure that they're answered later. We do have some discussion going on about some of our work in solid state transformers, which is great. But thank you, Dr. Hussain, for that overview of our research. And I do want to encourage all of our attendees to learn more about these projects at tomorrow's poster session. And thanks again to all of our main stage speakers.